you. Good afternoon, everyone. It's my great honor to be here with you today. I'm on behalf of vivo's research team to present some of vivo's research and technology advancements in the area of integrated sensing and communication, also known as ISAC. So today I will introduce ISAC in three major aspects. The first one is the use cases and system architecture, and then key technologies, and the third part is channel measurements and the prototypes. Okay, first is the use case and system architecture. The ISAC refers to one system to provide sensing and communication functions to utilize resources efficiently and even to pursue some mutual benefits. ISAC can provide spatial information about unconnected objects, as well as connected devices and their movements and surroundings. And ISAC will play an important role in many scenarios, such as low altitude zones, industrial automation, medical and healthcare, warehousing and logistics, and so on. And two examples here in the slides, the use cases are the personal health monitoring, such as sleep quality monitoring, and the intelligent transportation, such as the pedestrian detection and vehicle speed detection. Okay, so this slide is about ISAC system architecture. This is the overall diagram for the system architecture. At the bottom, you can see the chart includes 6 basic sensing modes, such as the base station monostatic, base station to base station bistatic, and base station to UE bistatic sensing, and so on. Totally 6 different modes. So there are various kinds of sensing use cases. The target of ISAC is to support all use cases through a unified measurement framework rather than case-by-case design. So at the top of the chart, you can see the sensing control function and sensing data processing function will be supported eventually by the network side. Okay. Regarding the different sensing modes, we have carried out some simulations to compare the sensing SNR performance between the base station monostatic sensing and UE to base station bistatic sensing for the indoor scenarios. You can see the right-hand chart. The simulation results show that the UE-based sensing can improve the sensing performance compared to the base station only monostatic sensing, especially in the poor coverage region. Okay, now I'm going to talk about some more detail about for the key technologies used in the ISAC. So this slide is about the ISAC waveform and signal pattern. So there are 3 typical directions for ISAC waveform design. First is waveform for communications, for example, the OFDM, DFTS, OFDM. The second is a waveform especially for sensing, such as FMCW. And the third one, relatively new, is kind of a newly proposed dedicated waveform for sensing, or for ISAC, such as OTFS. Regarding the sensing signal patterns, you can see the right-hand side compare with the regular signal patterns. The irregular signal patterns, such as Costa's pattern, is important because it can help to achieve better results with a lower overhead. Okay, this slide is about the multiband sensing. It actually refers to the joint acquisition and the processing of sensing data on different frequency bands, which can obtain more comprehensive and accurate sensing results. There are multiple directions technically for the multi-band sensing. So basically, we can do different sensing measurements for different bands, or the same sensing measurements for different bands, or we can do alternatively using the two-step sensing approach. So basically, for the two-step sensing, that means a lower band could be used for the coarse-grained or coarse granularity sensing, and the higher band with better accuracy for the finer grain sensing. And the frequency of multi-band sensing is actually, well, I would say the challenge of multi-band sensing is that there may be some initial random phase alignment problem due to the use of different frequency bands, which could affect the coherent processing. Okay, this is about the multi-antenna ISAC system. It's basically the integration of MIMO and ISAC. The typical hybrid analog or digital multi-antenna architecture for sensing would consist of two parts. So for the analog beamforming, it can generate a beam directed at the sensing target to obtain very good beamforming gain, and digital beamforming can form the virtual array to achieve a higher sensing resolution. Okay, well, this slide is about the coordinated multi-point sensing. Basically, compare with the monostatic sensing, the bistatic sensing involve more nodes for the sensing mechanism and can achieve a diversity gain. So furthermore, if introducing more nodes, it actually can be involved in the sensing process, which would create the so-called COMP system for ISAC. So in that kind of system, different levels of sensing data can be collected in one node to generate the final sensing results. The table here actually shows different level of sensing data. There is a trade-off always between the amount of sensing data aggregated and the sensing accuracy of the COMP ISAC system. And in order to achieve the optimum allocation of resources while meeting the sensing performance requirements, the resource allocation of sensing signal needs to be adaptively adjusted according to the sensing measurements. So this can improve the overall system efficiency of ISAC. The network side need to adjust the resource of power, time, frequency, and space parameters according to the sensing measurements, such as sensing SINR, measurement results of Doppler and latency, and so on. And one example is that you can see the right-hand side here when the target, basically the person, when he or she gets closer to the UE, that you can see that the density of the sensing signal can be reduced. Some adaptation there. Okay, this page about mobility management. So to ensure the continuous user experience of ISAC, the mobility management of ISAC is quite essential due to the movements of the sensing targets or the sensing nodes. Either way, the best sensing nodes for the sensing service need to be adjusted or changed. So this is similar to the handover of cell resection or the handover in the normal cellular communications. And the procedure of mobility management for ISAC would include the 4 steps. So the first is to determine if the conditions for switch of sensing nodes are met, and then to determine new sensing nodes. And thirdly is to send sensing context or configuration for new sensing nodes. And finally, to have the new sensing node start do the sensing job. Okay, so this slide is about some non-ideal factors related to ISAC. So basically, the sensing non-ideal factors are caused by imperfections in devices, which can lead to serious measurement errors, which would in turn affect the sensing accuracy. The sensing non-view factors typically include timing offset, carrier frequency offset, RF channel inconsistencies, and time domain random phases. And the corresponding methods to accommodate this kind of challenge would include common clock calibration, the CSI ratio of two antennas, and the reference path, as well as the round trip time based methods. Okay, during the ISAC, some of the information obtained from sensing may be quite private. So there's a risk of information leakage. Therefore, it is necessary to regulate the application of sensing by appropriate rules and processes, as well as adopting effective technical means to protect the sensed information and prevent the privacy leakage and other security issues. So this can be done, for example, through the sensing encryption, or we can enable or disable of the sensing function. We can also do some sensing obfuscating or sensing authorization and authentication. Now I will give some brief introduction on the prototype development work and the channel management work vivo has conducted so far. We have developed 3 ISAC prototypes, as you can see in this slide, that include the monostatic sensing, and you can see it's actually this prototype setup. And also, besides the monostatic sensing, also we have bistatic sensing prototype, as shown lower bottom and right bottom column there. So this one is the typical bistatic sensing, one base station, one UE, and this one involved with multiple UE in a coordination mode. Those prototype work in the sub 6 GHz band and with bandwidth of 100 MHz. And the sensing use cases include, respiration monitoring, range and velocity detection, and trajectory tracking of human. Here, basically, it's trajectory measurement result for the COMP ISAC sensing. And that one is the respiration monitoring case. Okay, so besides the prototype developments, we also explore the channel measurement. In this page is about when the user under test do the breathing. We check the channel measurement results for respiration, and the receipt power of the main multipass component generated by the human when this guy do the breathing. Basically, it can tell the difference for the power of the relevant path in the case of exhalation or inhalation, respectively. We also conducted a sensing channel measurement for the human body falling down. So these tests take place indoor environment as well. And the channel characteristics, for example, the delay and the power output are different depending on whether the people or the person was kneeling like this or falling down, facing to the ground. Yeah, that's basically all my presentation slides. Thank you for your attention.
Okay, thank you. Thank you, Xian.